All right. Before we get going, just a reminder of a few things. I put up a web work due date for this section 4.4 for Tuesday night. I also put up a new quiz last night, which is due. Whatever the date of next Sunday is, the 10th. Next, not a week from Sunday. And there's one due this coming Sunday as well. All right, so we had to leave this example in the middle of it. So we're trying to find enough information to graph it. We got domain, we got single intercept, the origin. We found out something from looking at the first derivative. Looks like we got that it increases up to x equals -1 and increases thereafter, which means we have a local minimum. Do we have any other local experiment? We didn't write down any other local experiment. Is it possible that there are others? I have some kind of non-committal head shakes, but no, it's impossible. Yeah. So we found exactly one place where the derivative is equal to 0. The derivative cannot be undefined anywhere because x is defined everywhere. E to the x is an exponential function, it's defined everywhere. So their product will have to be defined and continuous everywhere. So that's the only minimum. That's the only local extreme I can have. What else can we learn about this function before we start graphing it? We have a lot of information, but maybe some other things we can look at. We're going to have periodic behavior. We're going to have asymptotes. We're going to have exponential. So it's not periodic. Yeah, so it's exponential. So those things don't. Yeah, they're not periodic. So we can rule that out. What about symmetry?
Oh, it's going to be an even function.
Why is it even?
Because whatever, like if you plug in a negative value for x, isn't it still going to come up positive?
Let's see. If I have y equal to -x times e to the -x, is that the same thing that y was? I don't think that's even. But is it odd? So by definition, odd symmetry means this. F of -x equals -f of x. Do we have that condition? What would -x times e to the x be? So this is what f of -x would be. And if I just take this thing and make it negative, that's going to be -x times e to the positive x. So I don't think I have either type of symmetry. Like I'll admit though, my first glance was yes, it's going to be odd, but that fell apart. So I have no kind of symmetry, no periodic behavior. We looked at asymptotes last time. Let's do something else this time. And just to remind you, the things that I gave you all last time, that's not really necessarily a checklist that you have to hit every single one, but probably need some of that information if you're going to draw a graph. One more thing I'm going to ask us to get here. So we have a local minimum. I know that it's decreasing everywhere to the left of that point, increasing thereafter. Let's find out something about concavity. So how can I get concavity of this function?
Find double prime.
Find what?
Double prime.
Right, so we have y prime. So if we find its derivative, we can get the second derivative. I'm going to use product rule from this form here. So that becomes e to the x times 1 plus x plus e to the x times 1. So if I put all that together, I get e to the x plus e to the x plus x e to the x. So x e to the x plus 2 e to the x. Actually, let's do it better. X plus 2 times e to the x. So that's my second derivative. What can I learn about concavity from this thing?
Or is it set by equal to 0, and then you plug in values on either side.
So I set this equal to 0. What specifically are we looking for when we do that? Inflection points, right? So how many inflection points am I going to get off of that?
1,
Just 1, right? Where's it going to be?
-2.
-2. Just a reminder, why? What did I ignore and why can I ignore it?
E to the x can never equal 0.
E to the x can never equal 0. So, and we ran into that problem last week, right? Or last time. So same situation. We have a single candidate for an inflection point. Do I know enough to say that's an inflection point though? I don't think I do. What else do I need to understand to answer that question? Right, I need to, so, more times than not, it probably will be, but let's make sure. So what's the derivative? What's a good point to the left of -2 to look at?
3.
-3, how about to the right?
0.
0, always choose 0 if you can access it. What is the derivative equal to? Or second derivative equal to at x equals -3?
Wait,
It's gonna be negative, right?
yeah.
And again, I don't care what the number is, right? So I think it's when you don't even know what the number is, it's okay to just, well, that's first derivative, right? Come to this one, the one that actually helps. And e to the x. Is this always positive, always negative? Maybe either one, or it's always positive, right? So really, what you want to know comes exclusively from this. If x is -3, that's negative, right? And if x is 0, that's positive. So what have we learned about what happens if x equals -2? I don't want to, not slope really. What changes there? The concavity changes. So I believe I'm concave down on what interval?
Negative infinity 0.
Not 0,
-2.
-2. And then concave up on -2 to infinity. We okay with all that data?
Yeah.
Okay. Probably gonna ask you to repeat something to me because I didn't do slide from my progress. So we sketched the curve. We had intercepts, right? Or 1?
Yeah.
Origin?
Yeah.
Where do we find a local minimum?
At -1, -1 over e.
Okay, so -1 over e is about there, right? Okay, so we know we also know is that the absolute minimum of this function too? Can we say that?
Exponential, yeah.
I mean, I think we can say something, I think we have an even stronger way to say that for sure. Do we know what our function is doing up to this point? It's decreasing, right? What is it doing after? Everywhere, right? So I think that's sufficient to say that is the lowest point this function ever takes. We also said something about concavity, right?
Yeah.
So what was the concavity to the left of -2?
Down.
Down, okay, so it was down?
To the left of -2.
Okay, which means it was up afterwards, right?
Yeah.
Okay. Oh, now, see this, I'm having a hard time thinking about what's gonna look like. Let's do this. Where's our inflection point? We said it was x equals -2, right? So y equals -2, e to the -2, which is -2 over e squared, which is about there. And concave up, right? Do we agree that's concave up?
Yeah.
Okay. So what's it look like as I go to the left?
Where do we describe that?
Here's one thing we should probably look at. What happens here? The limit is x goes to -infinity of x e to the x. Go ahead.
How did you get -2?
We did that on the last slide. So that x equals -2 is the inflection point we got. And just a reminder, how do we get that inflection point?
Second derivative. Yes.
Yeah, so to set the second derivative equal to 0 and find the x values that make that true. So what's going to happen to my function as x gets really, really, really small?
Just make it closer to 0.
So they get closer to 0, right? So because of that, it's kind of like, it's hard to avoid the x-axis when already have points so close to it. But I think our function looks like this, right?
And that's it. Then that's concave down right there. Wow.
Yes,
Yeah, that's crazy.
yes. So let's look at a good technology generated graph as opposed to my sketchy hand one, but it's pretty close, right?
Yeah.
I believe that minimum is reflected, that concavity kind of makes sense to me. Something to kind of look for, which is not the easiest thing in the world to see, but if you kind of zero in around x equals -2, it's kind of approximating something linear there, right? Because the derivative is at that point, by definition, the first derivative is neither increasing nor decreasing. So kind of approximates linear in that little neighborhood. Marcus?
Yeah, I just have a question. So on the left-hand side, as x approaches it, you said the limit is 0.
Let's look. Let's zoom way out. What do we think?
Probably 0.
0, yeah. So as x goes towards -infinity, the x part of that clearly getting very, very negative. But what's e to the x doing? Basically, it becomes 1 over these numbers that are just growing and growing and growing. So no matter, it doesn't matter how big x gets, they're being squashed. They're basically being multiplied by something that gets nearer and nearer to 0. Any questions about that? All right, I had a third example in the slides. I am not going to do it in class, but it'll be on the slides if you want to practice it. The homework on this, I'm not sure who's looked at it. There are 2 questions. So, I mean, I think you've seen enough to answer all that's there. If I'm wrong, let me know. And I can definitely get you some help, but I'm confident you can do what's being asked. Okay, so moving on to 4.5. So again, just a reminder what chapter 4 is all about. Chapter 4 is all about basically don't really have much more to show you in terms of how to take derivatives. Now this is all about, why you can have that ability. Optimization is a very, very important thing to calculus in general, but for most of you who are going on to engineering, this is something that is extremely important. So basically trying to find the best case scenario of some situation, or worst case in some situations. So let's just dive into examples. We can, as we do, if you will kind of revisit, or reflect on what are we doing to solve these kinds of problems. So the first thing we're looking at is the title. Sorry. what are we done? Okay, so, not that far on. All right, I want to find two positive numbers whose product is 169 and whose sum is a minimum. So, optimization, I'm trying to find the best case scenario. Or some minimum or maximum case usually. What is the thing in this case that I am trying to optimize?
A minimum.
So it's a minimum of some sort, right? So what is that idea? Like, what is that value? What is the thing I'm trying to make as small as possible?
The product numbers.
So Solomon says the products, someone else said sum. I believe that both of those are involved here, but let's be careful. Which one are we actually trying to make minimum?
You can't change the sum, because you have to get 169, so it has to be the product.
Well, you can't change the product.
So yeah, I think, so we're saying opposite things, right? So 169, that's a constant, right? Is that the constant product of these two numbers or the constant sum?
That's the constant product.
That's the constant product, right? Are we okay with that? So we agree that would we agree then that the sum is the thing I'm trying to make small? Okay, so typically there are two things that arise from these kinds of problems. One is, what am I trying to optimize? Like, what's my real goal? So I'm trying to optimize the sum. I'll call that S. How would I find the sum of these two numbers? What does the sum mean?
Addition,
Yeah, you're adding together, right? What am I adding together?
two positive numbers,
Let's call them something.
A and B.
Cool. So one thing that we need to do is, if we're gonna start, making models for these things, give names to all the things that you need to have your hands on. So capital S is the thing I'm trying to minimize, so that's my sum. Give that a name. The sum is based on these two things, so those need to have names. This is the thing I'm trying to optimize. I want to make this thing as small as possible. That's really easy to do if it doesn't matter what A and B are, right? But it does. Like there are rules. I can't just say A is equal to pick your favorite negative number, do the same with B. What am I constrained by? Like what restriction do I have here?
You have to be above 0.
Okay, is there anything more than that? Isabel?
A times B must equal 100.
That's true, right? So we have something we're trying to optimize, but it's not a perfect world, so you're going to have some kind of restriction or a constraint. And in this case, that restriction is this idea, AB equals 169. We okay with that idea? So I have two ideas here. This one I'm stuck with, right? This one I'm trying to, clearly A could be 169, B could be 1. Probably doesn't make this as small as it could be. So I am trying to make this S thing as small as I could. I am looking for its minimum. How could I find the minimum? Marcus?
Couldn't you like run like a matrix where you have two, like all possibilities and multiplying them all together to find the least?
You could do that. How many possibilities are there for like A-B pairs?
A lot.
Infinitely many. So matrix might find that if you kind of restrain it's what kind of numbers you're looking at. But would we agree that S, capital S, is a function? So I'm trying to find the minimum value of a function. If I can find this derivative, what can I do with it?
And find the minimum of local minimums.
Yeah, how do you find local mins and maxes?
Say 0.
Right, so if I can treat S as a function, which it is, right? It's a function in two variables right now. It's based on these two things, which is not something we like dealing with. But we could do that, we could find the minimum. Right now, S is a function of two variables. Does it have to be a function of two variables? Can I simplify it a little bit? How? I know that S is related to A and B in that way. Are A and B related to each other in a way that I could take advantage of?
Yeah, and this second equation.
Right, so that second equation, you all pick. You want to solve for A or solve for B? A equals what?
A equals 169 divided by B.
So based on this, now I have this function, S as a function of B, right? Which is equal to 169 over B plus B. So now I have a function in one variable. We're really good at finding minimums on those things as opposed to finding minimums on functions that have lots of variables. So what can I do with function S now? Because again, let's go back to the original goal. What am I trying to do? Like, what's the whole point of this one sentence here?
Get the smallest S possible.
I want to get the smallest S, which is going to come from a specific A and B pair. So I want to make capital S as small as possible, which we described just a minute ago how we might find, since we can use a function to describe it. So what do I need to do to that function?
DEB,
DEB?
DEB, take the.
Right, yeah. So we're going to take a derivative with respect to B. So ds dB is equal to what? I'm gonna handle this part for you.
169 over B squared.
Missed something.
You gotta use quotient rule there.
You don't have to show use quotient rule.
Out of the phone. So I had to do some stuff.
I mean, it's the way it's written. I mean, kind of probably the way most of us, including me, it's like, oh, it's a fraction, it's quotient rule. But I'll remind you that you can rewrite that so it's not specific, it's not explicitly written as a fraction.
Negative 169 over B squared.
So negative 169 over B squared. And I'm looking for a minimum, so I want to do what with this derivative? Set it to 0. That is when local minima happen. Is at critical points, right? So, is there a critical point? So how do I find critical points in this thing?
Onward, is it?
Or where else?
Or does it exist?
Where is this derivative not going to exist?
At 0.
Do I even need to consider B equals 0?
Well, no, because it's not gonna exist.
Right. Also, I told you the numbers have to be positive.
Yeah.
So like, yeah, that's, we can recognize a critical value and then just move on because we don't care about that. So I need to find where this thing's equal to 0. So moving some things around, I get this equation. 1 equals 169 over B squared. What does that say about B?
B squared equals 1 divided by 169.
Not quite. I think it's just B squared equals 169. If you multiply both sides by B squared. So then I get B equals plus or minus 13, right?
Yep.
So,
It has to be positive.
okay, so then I can, and this is another thing that we need to be careful about with these problems. You might get answers that don't make sense to you, we don't care about. I said that B had to be positive, so B equaling 13 is the only thing I've gotten so far that makes sense to me. So how do I find two positive numbers? I found B. How do I find A?
I get back to
I'll do you one better, Solomon. So in the process here, I kind of came up with a formula that relates A to B, 13. So I think I have found that A equals 13 and B equals 13. Any questions on how we went about that? Okay, so yeah, let's do got time for a couple more, but yeah, let's do a few of these and we'll talk about we'll kind of try to construct this process. All right. So I have 360 feet of fencing and I want to build a pen that looks like that. What's the maximum area that the farmer can enclose? So what's the goal? Isabel?
Okay, so I propose the limiting factor is 360 feet, like that's the maximum amount of fencing you can use, so that's gonna, you can't have anything larger than that perimeter.
Okay, so the restriction has something to do with perimeter, right? Really is that the perimeter equals 360, right? So that's a good restriction. That's the thing that's that's the reason a maximum exists, is because I don't have unlimited material. Okay, so what other information is worthwhile to jot down here? The equation for perimeter. That's great, yeah, we need that. So how would we get an equation for perimeter here?
Is that 2x plus x? I don't know, I'm just confused by the diagram.
So basically, there's an outer fencing, right? But then it's got these interior fences. I'm trying to keep animals separate. So I wrote down the word perimeter, but it's not really perimeter that we're specifically looking at, right? So I think perimeter by definition just means the outer lengths. But really, we have these inner lengths where I got the fence there. So let's write down an unsimplified thing then. Let's get what's the outer perimeter first?
3x by 3y.
3x by 3y?
3x times.
How do you find perimeter again? What does it mean?
Oh, addition.
Right, so it's just lengths, right? It's just lengths. So 3x plus 3y. We agree that's the outer perimeter?
Times 2?
Times 2, right? You built me half of a thing with 3x and 3y. So yeah, I need the opposite sides too. That's the outer, like the outer perimeter. So how do I get those inner fences?
That's another 3x and another 3x.
Yeah, it's just, yeah, basically I'll not replace the 2 with a 3. I'll do plus another 3x plus 3y, right? So simplifying all that, I get 9x plus 9y equals 360. The second 3x. So basically this inner fence here, that's an x and that's a 2x, right?
Oh, okay.
Then that's a y and that's a 2y. So I think my constraining equation, my restriction, is 9x plus 9y equals 360, right? All right. What else do I need to keep track of here? What's the bottom line here? What is the thing I actually want to do? I'm trying to optimize something.
You're optimizing the largest possible area.
So I'm trying to maximize. So I'm gonna say the goal is to maximize the area. Okay, so how can I translate that into things that are useful for us? Area equation. What's the area of this structure in terms of my variables? What was that? This is also 3x times 3y. We okay with that? Yep. Length times width.
that.
Right, so this right here is 9xy, right? Okay, so I have my restriction. I have the thing that I'm trying to make large. In this case, I'm trying to make it large, not small. Where can I go from here? Right, so, yeah, one thing I'll point out is that in general, how do you find the maximum of some function? Not this function, but in general.
Values have.
You said the derivative is equal to 0, right?
What is it, maximum?
Well, that's what I was getting at. You said the derivative is equal to 0, right? But when you take derivatives, you gotta take it with respect to one variable. So I think this thing is not as we want it yet. So how can we reduce this area equation in terms of a single variable?
We take the value of x or y from the first equation and plug in that in the second equation.
Right, so something we can definitely do here. And I'm gonna take a shortcut just because I see one. We can say that 9x is equal to 360 minus 9y, right? I'm gonna substitute that for 9x in my equation. So 360 minus 9y times y. I guess I should call it AY if we do that. So I now have a function written in a single variable that I would like to maximize, right? So how can I find, and when I say I want to maximize it, I want to find where its maximum is. How do I find that?
You take the derivative and set that equal to 0.
Okay. What is the derivative of this function? It's dA, I'll call it dA dy. Do we have to do product rule?
Two.
I don't want to do that either. So if it helps, and I will not promise that it always helps, but if it helps to expand these things out, I would definitely do it. So instead of doing product rule, like that's a much nicer derivative, right? So what's the derivative of that?
Negative 18y, then
Negative 18y
plus 260.
plus 360. And I would like that to equal 0, which means y is equal to what?
Which 20?
Should be 20. One thing we didn't do in the last example that we should also make sure of. Do we know that y equals 20, that gives us the maximum? We hope it does, but what's the other possibility? It could be a minimum, so let's make sure it's not. How do we make sure that's actually a maximum?
1921.
Do what with 19 and 21?
Plug them into the derivative.
Okay, so that's a good idea. So let's look at the derivative. So y versus a prime. I know that at 20, the derivative is 0. I would like to know what it is at 19 and 21.
19 is positive and 21 is negative.
Okay, do we agree with that? That was fast. Yeah, I think I agree with that.
So then it is a maximum.
We okay with that? We have a maximum. So we found the maximum. Now let's be careful. What was the question I was actually asked?
Maximum area.
I want to know what the area is, right? Cool. So how do I find the maximum area?
Well, you have the original function, just plug in y, 20 for y,
Into what function?
into 9x plus 9y.
Not 9x plus 9y.
Oh, 9x y.
So yeah, what is 9x plus 9y? What did that give us? That was the perimeter, right? So that would give you a value of x, but I don't even, in this case, I'm not actually asking you for what that is. I just want to know what the area is. So in this case, I'm just going to go straight to whatever a of 20 is. So 360 times 20 minus 9 times 20 squared. So 7,200 minus 3,600. So 3,600 square what? Feet. Any questions there? Okay. All right. I have a rectangle bounded between the x-axis and this semicircle. All right. There's my kind of bad sketch. All right, so what am I trying to do with this in this situation?
Find the length and the width.
Find the length and the width. So yeah, I want to find those things. Based on what?
Based on having the largest possible rectangle.
So yeah, largest possible rectangle, and how am I measuring how large it is? So yeah, I mean, for all these, we're gonna have some kind of numerical thing that we can get a handle on that we're trying to maximize. So our goal is to maximize area. So if that's our goal, how can we proceed from there?
We set up an equation for area.
Okay, what is the area going to be equal to? So I mean, it's clearly going to be equal to length times width, right? So let's just leave it right there for now. So area is equal to length times width. What else am I, like, what am I constrained by here?
The
Can I just make this, can I just draw any rectangle I want?
No.
no, this is shit question method.
Yeah, so it basically, it has to have its corners on that semicircle, right? So, I mean, that was kind of how I drew it, but these points here. So the restriction is basically this is the equation that restricts me. Is the equation of that semicircle. Radical 49 minus x squared. Isabel?
Are you going to have to use like sine and cosine to get the?
I don't know yet. Maybe. So here's the thing, right now I have 4 variables to look at. I don't like that. So it'd be helpful if we could write some of them in terms of the others to reduce the complexity here. How would I find the length of this rectangle?
I look with the X.
How do I?
I look with the X.
Okay, so let's do this. These points right here, basically it all comes down to, you know, if we know where the points of this rectangle is, we can find its area, right? Do we need to know all 4 points, or can I get them all from if like I know 2 of them?
You only need to.
Do I even need 2?
Oh,
Let's call this one XY. If that's XY, what are the coordinates of the point below it?
X negative y.
I don't believe that.
0, 1.
What's the Y value on this point here?
oh, so X.
How about this point over here?
Negative x0.
Negative X0. And over here?
Negative x plus.
Negative XY. And you got those 3 others just from the one that I said, right? So really, we only need to know 1 point of this rectangle. But the reason that I wanted to go through that exercise is, now can we say something about the length and width of this thing in terms of X and Y? What's the length of that rectangle have? The length is 2x. You okay with that? The difference from x to the difference between x and negative x. So now my area is equal to 2x. What's the width of this rectangle?
Y.
Just y?
Yes.
Yeah, just y. So yeah, it's if it was inside of a circle, it'd be much more symmetric, but it's just 2xy. So now we have reduced our 4 variable monster into only 2 variables. Okay, so where do you want to go from here? Again, keep your eye on the finish line. Keep in mind what we're trying to actually do.
No, if you know the width, get yourself the equation, like the width just divides like the width.
We don't know the coordinates. We're trying to find them, right? Like I'm trying to find what x and y are. But based on what, Isabel?
Can we substitute the equation in our area Y? Or,
Okay, let's talk about that.
Oh, yeah.
Can we put this y in for this y? Is that true?
Yeah, because
What's Y? Sure.
What have we assumed about these 2 points? Where are they?
the same y.
Well, the same y, but what else do I know about?
They're on the-
They're on the semicircle, right?
which means that
Does that help you answer the question? Can I just use that y?
Yeah, you can.
So these points are in the rectangle, but they're also on that semicircle, which means for any x value, if I give you an x value, the y value is going to come out of here. So yes, now I have area in terms of a single variable. So a of x is equal to 2x times radical 49 minus x squared. All right, all good steps. Now what?
On the derivative,
And why are we trying to find the derivative?
because we've done it both times before.
Yeah, but why?
for the max.
Yeah.
So we're trying to maximize that function, right?
So we got to find the local max using, and then, yeah.
Right. So just if you want to know where a function has a minimum or a maximum, that is going to come from where its derivative equals what?
0.
Yeah. So in order to find that, you better have a derivative. So what is the derivative of this thing? What do we need to find this derivative? Do we need product rule?
2 root 49 minus x squared.
Okay, so let's stop there. How'd you even get this term?
That's just product rule.
The whole thing?
No, that's not the whole thing. That's the one.
Okay, so yeah, the derivative of the first function times the second function. I agree with that. I think the second part is going to be a little more involved. But product rule, yeah, is a good way to go. So plus 2x times
1/2
One over.
49.
49 minus x squared.
Nine times the inside, the derivative.
What's the derivative of the inside?
Negative 2x.
-2x. I'm missing something
Yeah.
important.
1/2 root x.
Oh,
Yeah, so this power right here should be -1/2, right?
2x over 1, no, 2x over,
So hold on, let me stop here. Are we okay with this? I know it's not simplified or clean yet, but I just want to make sure we're okay with how we got here. If anybody has any questions, let's take it. Okay, so yeah, let's do some cleanup. So 2 times radical 49 minus x squared. That goes away with that. So minus 2x squared over radical 49 minus x squared equals 0. We like that? Let's do this too. And because we're running out of time, I'm going to guess that some of you, if not many of you, are thinking you'd like to find a common denominator and simplify it like that. Let me offer this to you. I have the sum of these two things equals 0, right? From there, I can do this. Radical 49 minus x squared equals 2x squared over radical 49 minus x squared. From there, I can cross multiply both by the radical, however you want to think of it. But then that'll lead me to this. A magical world, but no radicals anymore. Are we okay with how I got there?
We got rid of the 2, didn't we? 2x squared, is it just x squared now?
Oh, yeah, that makes sense. That's why we're gonna get an answer that I didn't think was in there, so, nope. Yeah, good catch, thank you. So from there, we should get 2x squared equals 49, right? And finally, x equals 7 over radical 2. Plus or minus 7 over radical 2. Are we okay with that x value? Okay, so what question did we actually get asked though? We got asked from the length and width, right? Have we found either one of those things yet? We found the x value.
so you just plug that in, find the length.
What is the length if the x value is 7 over radical 2?
14 over 11.
The length is double that. So the length is equal to 14 over radical 2. What is the width? How would we find it?
49 minus 49 radical 2.
So I have, so I'll do a little work up here. The width is equal to y, right?
Yeah.
Which is equal to square root of 49 minus 49 over 2. Which should come out to 7 over radical 2. I believe that's right, but I also took some shortcuts because we're short on time, but I think I like this length and width. I was expecting it to be twice as long as it was high. Any questions here? Okay, so we got a couple more examples to look at for optimization. So we'll hold those off, hold those for Monday. But this is a really important thing for calculus. It's also pretty tricky, as you're probably noticing. So Yeah, we'll talk a lot more about it on Monday. All right, have a good weekend, everybody.